one more example today. This one is going to be for a ternary separation. So let's say we have 100 moles per minute of a mixture of benzene, toluene, ethylbenzene, and we are given a temperature and pressure. It is isothermally flashed. So flashing is a unit operation in which you rapidly decrease the pressure. To 100 millimeters of mercury, the initial composition was 40% benzene, 40% toluene, 20% ethylbenzene. We want to be able to predict the amount and the composition of two phases. So here we are assuming that there's going to be vapor-liquid equilibrium, which we have to double check, and we'll kind of double check that in the process of doing the problem. But the first thing that we might have to do, first let's draw a picture. Drawing a picture should always be the first thing to do. So let's say we've got a flash separator. We've got our feed stream. We'll assume that there's a vapor stream and a liquid stream. We need some flow rates. So we'll call this N1. That's 100 moles per minute. This is very similar to a material and energy balance problem, by the way. N2 is going to be our vapor product. And N3 is going to be our liquid product. And let's see, what other information do we have? We've got the initial composition. 40 benzene, 40 toluene, 20 ethylbenzene. We do not know what the compositions of N2 and N3 are. So I'm going to call it YB and YT for the unknowns. And then similar to how we did in MEB, I'm going to say Y of ethylbenzene is equal to 1 minus YB minus YT. And we'll reduce the amount of unknowns that we have. So remember, the variable Y is for mole fraction in the vapor phase. Similarly, we have XB, XT, and XEB, which is 1 minus XB minus XT. All right, now what we need to do is figure out what the relationship between the mole fractions of benzene is in the vapor phase and liquid phase, or the compositions of all the components. And for a ternary system, we can't do a TXY diagram because there are 3 components instead of 2. So TXY works because you can represent 2 components on a 2-dimensional diagram, but a ternary TXY diagram would need to be 3 dimensions. So what we have to do here is we have to assume a model. And for benzene, toluene, ethylbenzene, I'm going to draw the molecules in a second. So benzene and toluene we've seen before in this class. There's benzene, there's toluene, and ethylbenzene is a toluene, but with an ethane group instead of a toluene group. So we already know benzene and toluene interact somewhat ideally. We're going to assume that when you introduce ethylbenzene, that the entire system is ideal. So assume ideal, and that Raoult's law is the relevant model for this vapor-liquid equilibrium. So we can do this instead of with a TXY or a PXY diagram. We need a PXY diagram, by the way, because pressure is changing, not temperature. I need to include that in my diagram as well. P1 is 200 mmHg, T1 is 50 C, T2 is 50 C, and P2 is 100 mmHg. So again, we're not given what the equilibrium data is. We'll have to use Raoult's law. So let's go back to our roots in MEB and doing a degree of freedom analysis. I want to count the number of unknowns that I have in this system. So I've got N2, YB, YT is 3, 4, 5, and 6. So 6 unknowns. 6 unknowns, and how many equations do I have to relate those 3 unknowns? The one type of equation that you'll always have, well, I won't say always, you'll very commonly have this is a material balance. How many material balances will I have? Remember from MEB that you have one independent material balance for every species in the system. I have 3 species, therefore I have 3 material balances. What else do I have? I have 3 components, and I'm assuming that Raoult's law is holding for all 3. So I'm going to say my other 3 equations are my 3 Raoult's laws. 6 minus 3 minus 3 is equal to 0, and I can go ahead with writing my equations and then solving them. All right, so pause the video, see if you can remember from your MEB days how you would go about writing these equations. There are my three material balances. Those should honestly be very easy to you at this point. I've also got three Routs laws. So I've got B Routs law, which says YB times P, which I know what the P is, 100 mmHg, is equal to XB P star of B at 50C. And similarly for T, Routs law, and ethylbenzene, Routs law. So remember how this goes. We've got 6 equations, 6 unknowns. What I like to do is circle my unknowns in all the equations and look for any that stand out as being relatively easy to solve. My material balances have at least 2 unknowns, so I can't start there. And it's looking like I'm not going to have any equations with 1 unknown right off the bat. Now, if you notice, I did not circle the vapor pressures of the components. And why not? Well, it's true that they're technically unknown. I don't know what they are, but I would use Antoine's equation or Clausius-Clapeyron if I had data for it. And I could obtain what the vapor pressure is because I know what the temperature is. So I'm just going to give you those numbers. Vapor pressure for benzene is at 50C is 271.29 mmHg. Vapor pressure for toluene is 92.11 millimeters of mercury. And pressure of ethylbenzene is 35.16 mmHg. And now I've got a system of 6 equations, 6 unknowns. I'm not going to show you the mechanics of how you would go through solving this. Solver in Excel would be a good strategy here. So similar thing, I would just solve all these equations for 0, plug them all into Excel, and then solver them all equaling 0 subject to the constraints and subject to those 6 variables. Final answers, just so if you wanted to double check this, you could. N2, the molar flow rate of the vapor, is 77.5 moles per minute. And N3 for my liquid is 22.5 moles per minute. And the mole fraction in the vapor, you know what? Yeah, I'll give them to you. Y benzene is 4.66. Y toluene, oh, sorry, I switched. No, I didn't switch those. Y toluene is 0.392. And Y for ethylbenzene is obviously 1 minus these 2. X for benzene is 0.172. X for toluene is 0.426. So hopefully this gives you some context as to why you may need to know what's in phase equilibrium. This particular example was for an ideal system where we had benzene, toluene, ethylbenzene, 3 molecules that were very similar. This is a very uncommon situation. Most mixtures that you're going to come across are not going to be able to be assumed ideal, and they are not going to follow Routs law. So what we have to do is obtain a model. We have to model this vapor-liquid equilibrium such that we could solve problems like this no matter which mathematical model we have representing vapor-liquid equilibrium. So a common way that this is done is with a modified Routs law approach. And the modified Routs law is looking very similar. So it's YI is equal to gamma I xi P star of T, where this gamma is the activity coefficient. And it explains, it's kind of like the fugacity coefficient. So the further this goes away from 1, the less ideal we have. The activity coefficient is equal to 1 for ideal mixtures and not equal to 1 for non-ideal mixtures. And the next couple of weeks, Well, so we have next week, which is going to be the exam. By the way, this will be the last material that we cover for exam 1. So anything that I don't think I'm going to cover anything on Monday or Wednesday of next week. We'll mostly just review those days. I may have some videos for next Friday, but that obviously will be after the exam, so not covered on this exam. And then we have our midsummer break. But after that, the next couple of weeks are going to be all about figuring out how we go about modeling this activity coefficient gamma. So that's a preview of things to come, and I'll see you next time.